Alright, so far we have covered the concepts. We have seen how AI works in manufacturing, what kind of data machines generate, and how failures actually happen. Now we shift gears. This is the practical session. This is where we stop just understanding and actually start doing. We're going to take a real world problem from industry, use real machine sensor data, and step by step figure out how we can use AI to make better decisions. If you can do this well, this is exactly how AI is applied inside real factories. This activity is called machine detective, and the idea is simple. You're not just running code, you're acting like a data scientist inside a factory. Machines are failing without warning. Each failure costs 50,000 per hour, and your job is to figure out, can we predict it early enough to prevent it. Now let's go through the problem. Omnigear Manufacturing operates a precision machining facility. Machines are failing without warning, and each unplanned shutdown costs 50,000 per hour. You are the data science consultant. Your task is to build a predictive model that catches failures before they happen, using real sensor data collected from the factory floor. Let's understand how a typical data pipeline works. We always start by understanding the data, what each column represents, what is a useful signal, and what should be excluded. If this step is wrong, everything that follows will be wrong. Data garbage in, garbage out. Next, we clean and audit the data, check for missing values, remove irrelevant columns, and avoid things like data leakage. Then we move to feature engineering. This is where we create better inputs from existing data, capturing relationships that raw sensors alone don't show. After that, we explore the data using visualizations to identify patterns, trends, and early signals of failure. Once we understand the patterns, we train a model so it can learn how these signals relate to actual outcomes. Then we evaluate the model properly, not just using accuracy, but metrics that reflect the real objective, like detecting failures correctly and early. And finally, we translate everything into a decision rule, something simple and actionable that can be used on the ground. So, this entire pipeline is about one thing: taking raw data and turning it into a reliable decision. Alright, let's go ahead and open the dataset link. Before we start using any tools or building anything, it's really important that we first understand the data. Because the better we understand what each column represents and how the data is structured, the easier it becomes to process it correctly and get meaningful results. So take a moment, open the dataset, and let's walk through it together. This dataset contains about 10,000 machine records, and each row represents one instance of machine operation. Each column is basically a signal coming from the machine telling us something about its condition at that moment. Let's quickly go through the important columns. We have air temperature and process temperature. These tell us about the thermal condition of the machine. Then we have rotational speed measured in RPM, which is rotations per minute, which is how fast the machine is running. Torque tells us the force being applied during operation. And tool wear tells us how long the tool has been used, which directly relates to degradation over time. Now, these are your core sensor signals. These are what the machine is continuously generating. Then we have the most important column, machine failure. This is our target column. 1 means failure happened, 0 means normal operation. We also have failure types. Now this is where it gets interesting. Failures doesn't just happen randomly, they happen due to specific physical reasons. Let's break them down. TWF stands for tool wear failure. This happens when the tool has been used too long, typically between 200 to 240 minutes. So this is basically wear and tear over time. HDF, heat dissipation failure. HDF happens when the machine is not able to release heat properly. especially when the temperature difference is low and speed is also low. Think of this like overheating due to poor cooling. PWF, which is a power failure. This depends on torque and speed together. If the machine is operating at too low or too high power levels, it becomes unstable and fails. OSF, overstrain failure. This happens when the machine is under excessive load, basically high torque combined with tool wear. So the machine is being pushed beyond its limits. RNF, this is very interesting. It's a random failure. So this is rare, about 0.1% chance, and it happens regardless of conditions. This represents unpredictable real world noise. So overall, what this dataset is telling us is failures are not random, they are driven by physical conditions, and our job is to learn these patterns before their failure actually happens. One important thing to note is the critical note is called data leakage. This failure type column tells us why the failure happened, but we only know that after the failure occurs. So we only will use that later. We won't use it while building the model. If we use the failure type to build the model, then it will become a problem because we already have that it's failed and it's going to easily predict that it's failed. So that is a key thing to keep in mind. Now let's open Julius AI, and this is the foundational step. We're going to look at how Julius AI handles raw data right from the start. I've got a standard CSV file here, nothing fancy. We're just going to bring that into the environment. I'll just grab our dataset here, upload that. Now, rather than telling it what to do, I'm going to drop in a very simple high level prompt. Notice how I'm not asking for a final chart yet. I want to see the logic. I want the AI to tell me what it sees in the data. This is where the real value starts to show. It's not just a solution, it's an insight for us to take a better decision. So the file name is predictive maintenance data.csv. So you can see that it's running Python code. It's analyzing all of the columns and the rows, and it's starting to give a few insights. It's gone through all of the variables, including the ID and all of the dependent and independent variables, including the target variables. And you can see how it's already analyzed the target variables and what are the different failure types of different machines. Not only that, it also gives you future steps of what you could take. This helps you decide and think better while making the decision of what kind of model to train and what are the best features to select. Now we're going to go ahead and upload our predictive maintenance dataset, and we're going to give a very simple prompt. So we're going to follow the same data pipeline that we have: understanding the data, cleaning it, engineering it, exploratory data analysis, and then model building and evaluation, and then finally a rule-based decision making. Now we're going to work on the cleaning part. So you can see that I've uploaded my dataset. I can select a template for going and cleaning through my data. So I'm going to go through a simple prompt saying go through my data and suggest any cleaning steps to be taken and how can I fix it. So now as you can see, it's going through a Python script and understanding and analyzing the data and working on its particular task of data cleaning. What all happens in data cleaning? It could be missing values or it could be duplicate values, etc. How do we fix this? Duplicate values are fixed by either deleting rows, or missing values could be fixed by things like imputation. Here you can see it's gone through and analyzed it, and it's saying that the shape is 10,000 into 12 columns. Missing values are 0, duplicate rows are 0. So the data looks clean. This is a data which is a clean data set. So there is no issues in this particular data set. So it's also analyzed my target variable, which is the machine failure, and the types, which is binary, which is either failed or not failed. So it's already checked all of the requirements. So this is a more simple video to keep it more beginner friendly and easy to understand. But you can feel free to explore more and understand more about data cleaning and what all it includes. Also, another important note here is that the correct data type, whether it's an integer, it's a numeric value, or it's a categorical value, or it's words. So there are two types, categorical and numerical, and that's very important in deciding whether it's a regression problem or a classification problem. Well, also, just because there are numeric values in a column doesn't automatically make it a numeric variable. That's a common misconception because it could be ratings. It could be something like 1, 2, 3, 4, 5, where high is 5 and low means 1. So that is a collection of 5 categories. So that would be treated as a categorical variable. And if we were going to use that as a target variable, it would be a classification problem. But if there are classes which are more than 20 classes, then we could treat it as a numeric variable. Maybe like even temperature could be a categorical variable if we are treating it maybe like 26 categories, 0 degrees Celsius to 26 degrees Celsius. But let's say we want to treat 0 to 100 degrees Celsius, then we would treat that as a numeric variable and that would become a regression problem. And well, there's no hard and fast rule that it's only 20 and above 20 it's you can treat it as a numeric variable or below 20 it's a categorical variable. It depends on the data scientist. There's no hard and fast rule that it's 20 variables, but as a rule of thumb we keep it as 20 variables, but it's highly dependent on the situation and the problem at hand. So as we have a fairly clean data set, we wouldn't have to do any cleaning techniques in this particular set. If you want, I can apply cleaning in place and export a clean CSV is what it's giving an option. Or we can drop columns or add columns. That is coming to the next step, which we'll see next. Now let's see something which is really fundamental. I really want you to understand this. And once you see it, it'll stick with you through everything we do in this course. It's this. The more options a model has to choose from, the harder its job gets. Let me show you exactly what I mean. Start with the simplest thing, a coin flip, heads or tails, that's it. Even if you're guessing completely randomly, you're right half of the time, 50%. Not bad at all, right? Now let's move to a dice. Now you got 6 options or 6 faces, and that same random guess, it's only correct about 1 in 6 times. That's around 16%. You can feel that difficulty jump already. Let's take it one step further. A standard deck of 52 cards. I ask you to guess exactly one card that I'm thinking of. Now you're down to less than 2%, 1 in 52. Not because you got worse, but because the problem itself got much, much harder. And that's the core idea here. Nothing changed about your ability to guess. What changed was the number of possibilities. Fewer categories means easier prediction. More categories is harder prediction. This is directly relevant to how we think about machine learning problems. And if you want to push it to the extreme, move beyond categories altogether, predicting exact temperature or exactly when a machine will fail. That is regression. There are no boxes to pick from. Your model has to predict any value across a continuous range of numbers. The search space becomes essentially infinite, which is why regression is often more challenging than classification. So the simple rule is this. Binary problems are the most forgiving problems. Multiclass gets progressively harder but still doable. And continuous variable prediction or regression is often the most complex of all. Keep this mental model with you. We'll come back to this constantly. Taking raw data, combining it intelligently, and creating features that better represent real world behavior. Alright, Now that we've created better features, let's see how these actually show up in patterns when we visualize the data. Now that we've cleaned the data and created better features, the next step is exploratory data analysis, or EDA. This is where we start asking, what is the data actually telling us? EDA is essentially using visualizations to understand patterns, relationships, and trends in the data, because numbers alone are hard to interpret. But when you visualize them, patterns become much easier to see. Now we're going to use Julius AI for this. And this is where it becomes very powerful. Instead of manually creating each chart like we previously did, Julius can generate multiple visualizations for us very quickly. And not just one or two, it gives full range of insights. You've already seen this dataset earlier when we learned about EDA concepts, exploratory data analysis concepts. So the idea here is not to repeat everything in depth, but to give you an overview of what's possible when you use a tool like Julius AI. As you can see, there are histograms to understand distributions, bar charts to compare categories, line charts to observe trends, correlation heat maps to see relationships between variables. So instead of guessing what matters, we can actually see what matters. Now let's focus on one of the most important visuals, these line charts comparing working versus failed machines. What you're seeing here are two lines, one for machines that are working normally, one for machines that have failed. And that is very powerful because now we are not just looking at values, we are comparing the behavior between a failure machine and a good working machine. For example, if you look at air temperature, process temperature, torque, or tool wear, you'll notice that the line for failed machines starts to behave differently from the normal machines. Maybe it's higher, maybe it's more unstable, maybe it follows a different pattern. And that difference is the key. That's the signal the model will learn later. So, what these charts are telling us is failure are not random, they follow patterns. And if we can identify these patterns early, we can predict failures before they happen. You can notice the pattern for a failure machine is much different than a pattern for a non failure machine. So, if you know that anywhere values are going to be read in this range of a failure machine, then you can flag it as it's going to be failing. So EDA is not just about plotting graphs, it's about understanding behavior. And now that we've seen these patterns, let's move ahead and use them to actually build a predictive model. Now we've gone through the entire data pipeline. We've understood the data, cleaned it, created better features, and explored patterns. Now we move to the most important part, turning all of this into a predictive system. This step is called model training and then evaluation. This is where we use all the patterns we've discovered to train an AI model that can learn. When a machine is likely to fail, so instead of manually writing rules, we let the model learn from data. Now, again, we use Julius AI to guide us. We can give it a simple prompt like what models can we use to predict machine failure, and it suggests multiple approaches, things like linear models, random forests, or XGBoost. Now we're not limited to one method. We can explore and compare different models and their evaluation metrics in terms of error. Let's understand one more important one here, random forest. To understand that, first think of a decision tree. A decision tree works like a set of rules. For example, if temperature is above a threshold, go one way. If below, go another way. And it keeps splitting like this until it makes a prediction of the ultimate result, or whether it's a failure machine or it's a succeeded machine. Now imagine this, instead of one tree, you have many trees. Each tree looks at the data slightly differently, and then all of them vote together. We take an average of all of their mathematical averages. That collection of trees is called a random forest. Like the name suggests, collection of trees becomes a forest, a random forest. A random, why is it random? Because it's always randomly splitting at slightly different ways. So instead of relying on one rule, we rely on multiple perspectives, and that usually makes predictions more stable and more accurate. Now, when we train multiple models, we don't just pick one randomly, we compare them, and that's what Julius AI helps us do. We can see how each model performs and identify which is one of the best for our problem. Random forest right now is the best performing. But here, something important. We do not just look at accuracy because remember, failures are rare in this data set. It's only about 4% of the times. And if you rate always, even if it's good at 100 times, even if you say that the machine is going to succeed 100 times, you're likely to be 96% right because 96% of the times the machine doesn't even fail. So we are not just looking on getting high accuracy, but we're trying to actually get a machine failure. So even a bad model can show high accuracy. Instead, we focus on how well the model detects failures. That's what actually matters in a real factory. And now we come to the most important outcome, not the model, the decision. Because in real world, no one's looking at confusion matrices or probabilities. A technician needs a simple rule. Something like if failure probability is above this threshold, trigger maintenance. This is called rule-based decision system. So the entire pipeline leads to this raw data, you get insights, then model, then decision. And that final decision is what creates real impact. Because AI is not useful until it helps someone take action quickly and confidently, even without statistical knowledge. And that's how we go from data to real world decision system. So what you're seeing here is the final outcome of the entire pipeline. We're not just predicting whether a machine will fail. We're also identifying what kind of failure it is, and more importantly, what action needs to be taken. So if the model detects something like a toolware failure, it directly suggests inspect or replace the tool. If it's a heat related issue, it points towards cooling, airflow, and temperature imbalance. And this is where AI becomes truly useful in the real world because the technician doesn't need to understand the model or the math behind it. The system is continuously monitoring, detecting patterns, predicting failures, and then translating that into a clear but actionable rule. So instead of checking everything manually, the technician can directly focus on the exact problem area. That saves time, reduces downtime, and makes the entire system much more efficient. And this is exactly how AI is used in manufacturing environments, not just to predict, but to assess decisions and actions. So as you move forward, keep experimenting, keep exploring, try different data sets, try different approaches, and more importantly, always follow the data pipeline because each step from cleaning to feature engineering to modeling and evaluation plays a critical role. And finally, go ahead and complete the assignment. Focus on your reasoning, not just the answers. Good luck and keep tinkering.